Howdy, my name is Parker Simmons.
Erica Hubner.
Michelle Creek.
Jessica Watson.
And for the Texas A&M Engineering Project Showcase 2020, our team is here to present the CoRe board.
Traumatic brain injury, or TBI for short, is the leading cause of death and disability in children. In fact, each year, over 500,000 children were admitted to emergency rooms in the U.S. for traumatic brain injuries. While many impairments left by TBI lack a quick cure, the affected children are treated in rehab clinics that seek to improve their visuospatial and visuomotor cognition through rehabilitative therapies. Current medical devices, however, do not meet the needs of pediatric patients and make the rehab process challenging for the therapist as well. Existing rehabilitation boards like the Dynavision are not size adaptable for children, offer little versatility for patients with varying abilities, and require manual data tracking.
One of the first steps in the engineering design process is evaluating who our users are. And after we determined who our users were, we came up with some user needs. Our users are patients who require therapy and rehab specialists who are administering the therapy. For our user needs, our device needs to be adaptable for patients ages 4 through 23. Our device also needs to be able to be used by patients who have a physical disability, for example, a wheelchair or on crutches. Our device is going to have randomly lit LED buttons that the patients must be able to press to extinguish the light. Our device also needs to be different because it needs to be able to track patient data and provide therapists with storable data that is trackable from week to week. Some market drivers for our device. We believe our device will do well in the market because it facilitates rehabilitation in pediatric patients and is easy to operate, which overall streamlines the overall rehab process.
Based on the user needs, our team developed a 9-module button board with the adaptability required for pediatric patients. The 9-module design maximized adjustability, simplicity of assembly, and therapeutic capacity as compared to a single module design or a design with fewer number of modules. The design has both an adjustable height and adjustable size. Furthermore, the device has multiple modes of use and the ability to track patient data. This differentiates our device from existing ones such as the Dynavision and Reflection Edge. The device's electronic components will be comprised of 3 Arduino Megas, individually addressable RGB LEDs, and simple 4-prong tactile switches. Arduino Megas were selected to control the device because of their high processing power and large number of input-output pins. The Arduino will be operated in concerted effort using daisy chaining. Through daisy chaining, 1 writer Arduino will run the software. The remaining 2 reader Arduinos will provide the writer with input and respond to its outputs. The schematic you can see on this slide illustrates how Arduinos can be wired for reader-writer communications using serial ports. Individually addressable WS2182B RGB LED breakout boards were selected for illuminating the device's buttons. The breakout boards are able to be chained together and operated using 1 Arduino pin, as you can see in this image. The LED breakout boards will remain addressable when chained, so specific LEDs within the chain can be targeted. This means that all 81 of our device's LEDs will be able to be operated with 1 pin. The number of pins and computing power required for our device's operation are thus vastly reduced when compared to what they would be if we were using standard 3-prong RGB LEDs. This slide highlights the basic electronic components for our device's buttons. Miniature breadboards were used to contain the button components, which consist of a tactile switch and an RGB LED breakout board. A standard wiring configuration was established for each miniature breadboard to allow for quicker troubleshooting and simplified assembly. Currently, the electronics for 9 buttons have been assembled, and the materials available for device expansion when circumstances allowed. The device's software was constructed in Arduino and processing. Currently, the device has 5 operation settings. In the self-paced settings, a light illuminates, the patient presses the illuminated button, the light extinguishes, and a new button lights up. In the program-paced settings, a light illuminates and remains illuminated only for a limited user-provided time. If the patient does not press the button before the preset time, the light extinguishes and a new light is illuminated. Finally, in the stop and go game mode, buttons illuminate in green and red. If a button is green, the patient must press it as fast as possible. If a button is red, the patient must not press it. In addition to a multitude of settings, our device is able to track and store the accuracy and response time of button presses. Data will be exported to a simple Excel file, which can be stored to monitor patient progress over time. A basic user interface for the device has been designed using processing, and the Arduino code is ready for expansion to all 81 buttons as soon as circumstances allow. This video highlights our self-paced white button mode. Basically, a white button illuminates in white, the user presses it, it extinguishes, and a new randomized button lights up. This slide demonstrates another self-paced settings, but with our rainbow color mode. In our rainbow color mode, button location is not the only thing randomized. Our light color is also randomized. Finally, in our stop and go mode, when buttons are green, patients are expected to press the buttons as fast as they possibly can. However, when a button turns red, the patient must avoid pressing that button.
All of the electronic components will be housed within a high-density polyethylene module. Each module housing will be 12 inches wide by 12 inches long by 2 inches tall. Each module will house 9 button assemblies. Each assembly will sit on a platform that will allow the button to be lifted high enough to protrude from the module front, as well as provide a space underneath to house the Arduino microcontroller. 3 of the 9 modules will each house a controller. The space between the platforms will be used to organize the wires that connect each individual button breadboard. The breadboard for each button will sit underneath the button base between the springs. The button design itself has evolved over time to better match the board design and function. The initial design included 3D printing a button with a simple circular cutout to allow the LED light to shine through from below. We realized that this cutout would not allow for the light to be seen easily unless the patient was standing directly in front of the opening. The next design attempted to address this by incorporating an expanding cone view. We also added a cutout on the bottom highlighted by the red arrow that would have placed the LED closer to the opening. Even with these changes, the LED was not easily visible and often was blocked by the plastic of the button. The current design tries to account for the lack of visibility by incorporating transparent materials into the design. The button is composed of 2 components, a vacuum-formed button cover and a 3D printed base. The base retains a similar design with 4 symmetrically placed pegs, but increases visibility by printing with translucent PLA. The button cover will be vacuum formed using clear 0.06-inch thick PETG plastic. The plastic will be rigid enough to press repeatedly and is compatible with the harsh hospital cleaners. The button height of 1.25 inches from the front of the module was determined because the button needed to extend beyond the face of the module so that the patient will be able to feel a difference between the board and the button. And when pressed, the button does not retreat all the way back into the board, which would prevent it from getting stuck should the button fall out of line. Once all the components are assembled, they will be attached to an aluminum frame. Each module will be attached to an aluminum tube that connects to a central metal plate. Each of the 4 corner tubes have concentric tubing that allows for diagonal expansion. The 2 red arrows show the location where the back plate will attach to a standard rolling TV frame. The collapsed interactive range is 3 feet by 3 feet, and when fully expanded will allow for a 5 feet by 5 feet range to be tested. This meets the needs set forth by the sponsors for an adjustable therapeutic interface.
For our device, there is a lot of engineering analysis that must go into the project. For the chemical testing of the materials, we had to use a harsh cleaner with a cover top, and we determined that with a cleaning material over 55% isopropyl alcohol on both PETE and PETG, we determined that after days of analysis that PETG was the correct way to go. Another example of test we did was creating a force body diagram to understand that our frame will not fall over. Our force body diagram indicates that our frame can withstand up to 90 pounds of force before tipping over on its side or on its back. Each button also has to be pressed with at least 5 pounds of force before it will be recognized as being engaged. For the validation test, we used a lock test, a button test, a cleaning test, and an adaptability test to check whether our specifications met our customers' needs. For the verification process, we used an expansion test, a corrosion test, a biocompatibility test, a stability test, and a tensile test to ensure that our software was met by our specifications.
One important consideration to make with any engineered device is marketability. Raw materials for the core board cost a total of $1,600, including the metal framework, module covers, custom buttons, and electronics. The manufacturing capabilities needed for this device include access to equipment such as a CNC lathe, water jet, 3D printer, laser cutter, and vacuum former. We estimate that the cost of these manufacturing services would add up to a total of $3,500 per device. When compared to competing devices, our device is a lower total cost and offers far more adjustability for pediatric TBI patients. Overall, the core board meets the needs of our target market in a cost-efficient manner. Thank you for watching.